Hello everybody. In this video we're going to solve one more example on the mass balance on reactive systems using the two methods that we discussed last two videos, which are the extent of reaction method and the atomic balance method. This example is going to be similar, but it's more detailed. We have here two equations or two reactions, and we have more additional relations which will make the problem more more interesting. So this is something that we will discuss here, and it's always nice to see how the solution is different from the extent of reaction method to the atomic balance method. So the example is about methane combustion. Combustion is a reaction. It's a reaction which produces a lot of heat, but it's still a reaction between a fuel and oxygen, and it can be complete combustion, meaning that it produces carbon dioxide, all carbon converts to carbon dioxide, or incomplete combustion where it produces carbon monoxide. So the reactor feed contains 7.8 mole percent methane, 19.4 mole percent oxygen, and 72.8 mole percent nitrogen. So these are the mole fractions in the feed stream, and the conversion of methane is 90%. So this is one relation that we know. And the second is that the gas leaving the reactor contains 8 moles of carbon dioxide per mole of carbon monoxide. So this is an additional relation between the number of moles of carbon dioxide and carbon monoxide in the product stream. We need to carry out degrees of freedom analysis and then calculate the composition of the product stream using the two methods, the atomic balance and the extent of reaction. So we will start with the first method, which is the atomic balance method, and here we have the flow sheet with all the variables, and I put the additional relations as text. I'm not converting them into equations now, but I have them as relations. I know that these are relations. So for the degrees of freedom, the number of variables here are 3 and 6 in the product stream, so they are 9. And again, I know sometimes this is kind of confusing, but in the extent of reaction method, we include the reactions, but as variables. But in the atomic balance method, the reactions are not included because we don't write the extent of reaction as part of the balance equations. So we have 9 variables. We have 2 given variables, only 2, and we have the number of equations is equal to the number of elements involved in this system. So we have carbon, hydrogen, oxygen, and nitrogen. So we have 4 atoms or four elements, which means that we can write 4 balance equations. And the last thing is the additional relations, which are these two relations. So we have 9 minus 8, which is 1 degrees of freedom. This system is not solvable with the given information, but we don't have any given flow rate, so we can assume a feed basis of 1000 kilomoles per minute, for example, and this makes the degrees of freedom is equal to 0. So now we can proceed with the solution. The solution will be based on these 6 equations, the 4 balance equations and 2 additional relations. So if we start with the balance equations, then we can write the balance equation on methane. We have methane only in carbon only in balance on carbon. The carbon only is available in the feed stream in methane. So it's number of moles of methane times 1 is the number of moles of methane in the feed equal the number of moles carbon in the feed equal the number of mole of carbon in the product, which is in methane, carbon dioxide, and carbon monoxide. In the atomic balance method, we have to be careful that you take into account all the compounds that contain this element, especially if you have a big list of compounds in the product stream or in any of the 2 streams. Then this is something that needs to be done with care. Anyway, so writing the balance equations on carbon, so we have 78 equals the methane times 1 plus carbon monoxide times 1, number of moles of carbon dioxide times 1. So this is the first equation. Balance on hydrogen, it's 4 times the number of moles of methane equals the 4 times the number of moles of methane in the product, plus hydrogen is here, so 2 times the number of moles of water vapor, and this is another equation. The third equation is for oxygen. Oxygen is only available here, so it's 194 times 2 equals the number of moles of oxygen in the product stream times 2 plus the number of moles of carbon monoxide times 1 plus the number of moles of carbon dioxide times 2 plus number of moles of water times 1. And again, this is something you need to be very, very careful about. If you miss any of them, then all the results would be wrong, because the equation is not written correctly. Finally, for nitrogen is going to be very straightforward. Nitrogen is not part of any reaction, so it's going in and out of the reactor without any change. So the number of moles in equals the number of moles out. So it is 728 kilomoles per minute. Now we can we are done with the 4 equations, and we can start using these 2 relations. So we have now 5 unknown variables, which are the 5 components here, or all the components here excluding nitrogen, because we calculated nitrogen. So we have 3 equations and we have 2 more. So we have 5 variables and 5 equations. So we can calculate the unknown variables. For the first additional relation, it is the methane conversion, which is a relation between methane in the feed stream and the methane in the output stream. So it's N minus out over N, which would be 78 minus the methane in the product over 78 equals 0.9. So it's going to be 7.8. Or you can think of it in another way. So the way we did it here is the systematic way. There is another way, which is the logical way, that you know that 90% of the methane is consumed, so what is left is 10%. It's very, very, very simple. So you have only 10% left, which is 7.8, 10% of 78. The second relation is the gas leaving the reactor contains 8 moles of carbon dioxide per mole of carbon monoxide. So this is the ratio of the number of moles of carbon dioxide to the number of moles of carbon monoxide in the product stream. Okay, so we can write it as N carbon dioxide over N carbon monoxide equals 8, or the number of moles of carbon dioxide is 8 times the number of moles of carbon monoxide, or the flow rate of carbon monoxide in the product stream. Now we have 5 equations and 5 unknowns. We can solve them together or simultaneously, and we can get the product. And if you look at this first, it's not an equation, it's already a calculated variable. So you can substitute with methane here, and here. There is no methane here. So in these 2 equations, we can directly calculate the number of moles of water from the second equation, and taking this equation, which will have only two unknowns, which is the number of mole of carbon dioxide and carbon monoxide, and this equation, we can solve them simultaneously to calculate both variables. And finally we will end up with water, which we can calculate from the third equation, and we can get all the unknown variables. So this is the the solution using the atomic balance method. For the same problem using the extent of reaction method, we have I put the same flow sheet, all the reactions and all the relations. And if you notice here, I didn't put the reactions because they are not of interest in this method of solving the mass balance or solving the system or doing the mass balance calculations. In the case of extent of reaction method, it's important. So this is why I put the 2 reactions here. We need to know the coefficients of each one of the components in the 2 reactions. So this is a very, very important thing. So this is something I recommend also, that you put the equations beside the additional relations or the rest of the information that you want to include. Okay, so for the reactor, let's do the degrees of freedom first. We have 3 components here, we have 6, and we have 2 reactions. So it's going to be 9 plus 2. Number of given variables are 2. I put here the values after adding the bases of 1000 kilomoles per minute. So this is after the bases, but before the bases they are only 2. And then the number of equations equal the number of species. So we have six species here: methane, oxygen, nitrogen, carbon dioxide, carbon monoxide, and water, and the same 2 relations. The relations don't depend on the method of solving the problem. They are relations. It doesn't matter which one of them is or which method we are using. So they're still going to be the same relations with the same way of expressing them. So the degrees of freedom is going to be 0 after the bases, as I just said. So for solving this problem, we will start with the additional relation, which is the conversion. For the atomic balance method, it was possible that we start with the conversion, but still we will have the same procedure for solving the problem. So it's not making a big difference. But if I start with this, we will get the same result for the number of moles of methane in the product stream, which is 7.8 kilomoles per minute. And now we can write the balance equations. We can write the balance on methane. So the methane in the product is going to be equal, or will be equal to the methane in the feed. It's present in the two reactions, so it's multiplied by the coefficient in the first reaction, or plus the coefficient in the first reaction multiplied by the extent of first reaction, and the same for the second, which is this. It's -1 in both cases because it's reactant with one coefficient of 1, so it's -1 and -1, so it's minus xi1 minus xi1, so xi1 minus xi2, I'm sorry, so xi1 plus xi2 equals 70.2. The balance on oxygen is, or let's do carbon monoxide. So carbon monoxide and carbon dioxide are going to be very simple. There is no carbon dioxide and carbon monoxide in the feed, so it's equal to 0 plus the coefficient, which is +1 times xi1. This is carbon monoxide, and carbon dioxide is going to be the same. It's xi2, and now we can use the additional relation, which is this relation, to find the relation between xi1 and xi2, and using this equation and this equation, we can simply get the value of xi1 and xi2. Okay, and now I know the number of moles of carbon monoxide and number of moles of carbon dioxide in the product stream, and we can calculate the rest of the variables. Once you calculate the extent of reaction, you can do anything, or you calculate everything. It's not do anything. You can calculate everything. So the balance in oxygen, it's going to be this is O2, not O, but the number of moles of oxygen in the product equals the feed, 994. It's -3/2 xi1 minus 2 xi2, which we'll give this number. For nitrogen is going to be the same, in equals out, so it's going to give the same result. And for water, I think we didn't do the balance on water, so it's going to be the feed, which is 0 plus 2 xi1 plus 2 xi2. So we now calculated everything. So this is the summary of the results as flow rates for the feed and for the product, and the mole fractions or mole percentage. You'd see here nitrogen is the dominant in both cases because it's much more than the rest of the components as number of moles. Okay, so this is something that you would notice, and this is something that's very, very common in the combustion reactions because combustion takes place in air. This is something we will see in like 4 or 5 videos, inshallah. So I'll stop here. Next time we will continue talking about the reactive systems and the things related to the having multiple unit systems or doing balance in multiple unit systems. So I'll see you then. Goodbye.